So we have the definition of limit up here. We're in the middle of proving this theorem that says that a function converges, or the function has a certain limit if and only if for all sequences, if the x's go to the c, then the f of x's go to L. So we're going to assume the thing about the sequences, and we're going to prove that the limit of the function is L. But I'm going to do that by supposing towards a contradiction not. What that means is that f does not have the limit of as x approaches c is not L, which means there exists an epsilon naught instead of for all epsilon naught. There exists one such that no matter what delta you pick, there will be some x in the domain such that x minus c is less than delta, but f of x minus L is bigger than or equal to delta naught. Right? Normally you want it less than epsilon, but here we have it bigger than or equal to epsilon because I'm supposing that doesn't have a limit. Well, here's the basic idea. I'm going to take a picture of the graph, let's say, I don't know, right here. Here's my C, and let's suppose L is way down here. Right? Because I'm assuming that doesn't converge. I'm going to produce a sequence such that x sub n goes to C, but the f's do not converge to L. So here's what we have. We have L minus epsilon naught right there, and L plus epsilon naught right there. So really, what this says is that there exists an epsilon naught such that no matter how close you get to C, there will always be some x that's not contained in that little cylinder, that red cylinder. So here's what we're going to do. We're going to look at, since it's true for all deltas, we're going to look at a whole list of deltas. Each of these deltas is going to give us an x1, x2, x3, x4. These are going to converge to C, but f of x, so it'll also give us these. But these will not go to L, which is going to contradict 2. And how should I pick this? Well, I'm going to let delta 1 equal 1 over 1, delta 2 equal 1 over 2, delta 3 equals 1 over 3, let's change this to delta n, x sub n, f of x sub n. That's just going to equal 1 over n. Here's how you pick it. So here's C plus 1, here's C minus 1. Right? No matter what epsilon you pick, or no matter what delta you pick, there will always be an x in there that's close, that's within that's close to C here, but is far away from there. So maybe right here we get an x1. It's in this interval, but notice the f value is outside of this red cylinder. So that's my x1. Next, what I'm going to do is I'm going to let delta 2 equal 1/2. So I'm going to look at C plus 1/2, C minus 1/2, and then that says for all delta, including delta equals 1/2, there exists an x that is within 1/2 of C, but again, the function lies outside. So that gives me another, maybe that gives me an x2 that's right there. But if you go up, we're still far away. So that gives me an x2. And finally, I'll jump down here to the n. So here we go. C plus 1 over n, C minus 1 over n, and I can find an x sub n in there such that f of x n minus L is bigger than or equal to epsilon naught, is outside of that radius. So I have all these x's, and pretty clearly they should converge, right? Because right, by the Archimedean principle, there exists an n such that, right, let epsilon equal 0. There exists n such that 1 over n is less than epsilon. Then what we have is x sub n minus c is less than or equal to 1 over n, less than or equal to 1 over capital N, which is less than epsilon, for all n bigger than or equal to capital N. So the x sub n go to C. But clearly, all of our f's were outside this epsilon range. But f of x sub n does not go to L, and we're done.